In this video, we'll talk about using exponential and logarithmic models to describe natural phenomena such as growth and decay. The simplest way to model growth and decay is to use the exponential model. The exponential model uses an exponential function. A at t equals a sub 0 times e to the kt. A sub 0 is the initial amount, because if you plug in t equals 0, you get a sub 0 times e to the 0. E to the 0 is 1. So a evaluated at t equals 0 is equal to a sub 0. So that's why it's called the initial amount. We often think of t as representing time. So when t is equal to 0, we have the starting amount, or the initial amount. We can either have exponential growth or decay, and it depends on the value of this k. If k is positive, then we have exponential growth, which is represented in a graph that increases very rapidly. On the other hand, if k is negative, then we have exponential decay. Exponential decay is the same graph except reflected through the y-axis. So instead of increasing rapidly, it decreases rapidly. Let's remark that a at t defined in this way, a sub 0 times e to the kt, is an exponential function with base b equals e to the k. And we can see that if we just write it out. A at t is equal to a sub 0 e to the kt, just rewriting the function. But using the properties of exponentials, we can write this as e to the k raised to the t. So this is a sub 0 times b to the t, where b is equal to e to the k. So this is an exponential function. We write it in terms of e, but really the base is e to the k. That's why if k is positive, then b is equal to e to the k is greater than 1. So that's why we have growth. On the other hand, if k is negative, then b equals e to the k. This is now a negative number in the exponent. This is less than 1, which gives us decay. So, for example, in the case where k is greater than 0, you can have b is equal to e cubed is greater than 1. But if you have b is equal to e to the negative 3, that's 1 over e cubed, and that's less than 1. Let's look at an example. Suppose cells of a certain bacteria colony divide into 2 every 10 minutes. So that means after 10 minutes the population doubles. Assume the initial population consists of 20 cells. If the population size after t minutes is given by an exponential model, a at t is equal to a sub 0 e to the kt, what are the values of a sub 0 and k? Well, a sub 0 is the initial population, so that's, we already know, going to be 20 cells. But let's just write everything out. So a at t is equal to a sub 0 e to the kt. Now what is it that we know? Well, we know that the initial population is 20 cells. So that tells us that a at 0 is equal to 20. And so now we can show directly that that's a sub 0 by just computing in the formula. A sub 0 is equal to, or a evaluated at 0 is a sub 0 e to the k times 0. But e to the k 0, that's just going to be 1. So this is just a0. So that's how we know that a0 is equal to 20. Here we're just using the fact that the initial population consists of 20 cells. And here we're using the fact that a sub t is given by this exponential formula. So that identifies a sub 0 for us. What about k? We need to identify k. So we know at this point that a at t is equal to 20 e to the kt. So how is it that we're going to figure out what k is? Well, we need some additional piece of information. And we do have an additional piece of information. Namely, we know that the cells of the bacteria divide into 2 every 10 minutes. So that means after 10 minutes, the population size is doubled. So we know that after 10 minutes, we know that the population size is doubled. It started at 20, and then after 10 minutes, it doubles. So after 10 minutes, it doubles from 20. That makes it 40. So A evaluated at 10 is 40, but we have this formula here that tells us what A at t is. So plug in t equals 10 into this formula. So that gives us that A at 10 is equal to 20 e to the k times 10. But we know that this is equal to 40. Now our objective is to solve for k. So the first thing I want to do is divide everything by 20. So we have e to the k times 10, or 10k, is equal to 40 divided by 20 is 2. So we want to solve this equation for k. That means getting the k out of the exponent. We can reinterpret this exponential as a logarithm, or this exponential equation as a logarithm equation. Because what are we reading here? E to the 10k is equal to 2. That means 10k is the power of e that gives us 2. So 10k is the power of e that gives us 2. Of course, log base e has another name. It's the natural logarithm. So this is ln of 2. So 10 times k is the natural logarithm of 2. So k is equal to the natural logarithm of 2 divided by 10. And that's the other thing that it asked us for. It wanted us to find the values for a sub 0 and k. So now we know that the formula for a sub t is equal to a sub 0 times e to the k, which is ln of 2 over 10, times t. And this is our formula. Now it asks us to find the number of cells after 1 hour. In order to do this, it will help if we actually have our formula here on the screen. So it's right there. Let me just rewrite it. A at t is equal to 20 times e to the ln of 2 over 10 times t. There's actually another way to write this which might be useful, because we can write this as 20 times e to the ln of 2 times t over 10. Now why would we write it like this? So far all I've done is I've just rewritten ln of 2 over 10 times t as ln of 2 times t over 10. So I've just rearranged these a little bit. But here we have an exponential where it's a base raised to a product of exponents. So we can rewrite this as 20 times e to the ln of 2, and all of this raised to the t over 10. So why would this be helpful? Well, first of all, let's verify that we did something we're allowed to do. Here I have an exponential raised to an exponent. So I multiply the exponents together, and that's how I end up with the ln of 2 times t over 10. But the reason I would do this is that e to the ln of 2, using the cancellation rules, is just 2. So that tells me that a at t is equal to 20 times 2 to the t over 10. So now if I want to compute this after 1 hour, but t is in minutes, so if this is a evaluated at 60, this will be equal to 20 times 2 to the t equals 60 over 10. So that's 20 times 2 to the 6. And 2 to the 6 times 20 will give us 1,280. So the number of cells after just 1 hour is 1,280. So now we're asked, after how many minutes will the population reach 1 million cells? So for this problem, we want to find t so that a at t is equal to 1 million, which perhaps we want to write just for brevity as t to the 6th. Okay, so we have a formula for a at t, and let's go back to our base e version of this formula. So it's going to be 20 times e to the ln of 2 over 10 times t. And we want to solve this for t so that we get 10 to the 6th. So we want to solve for t. So that's our objective, is to figure out what this t is in this equation. So the first thing to do is isolate it as much as possible. So we're going to start by isolating the exponential by dividing everything by 20. So e to the ln of 2 over 10 times t is equal to 10 to the 6 over 20, which is 50,000. So now what do we do? Our objective is to get this t out of the exponent. So we can rephrase this in terms of a logarithmic equation, or we can simply apply the natural logarithm to both sides. So the natural logarithm of e to the ln of 2 over 10 times t is equal to the natural logarithm of 50,000. Now all of this is in the exponent here, so maybe I should just move it up just a little bit so it's more clear that it's in the exponent. Okay, so on the left side here, the ln and the e will cancel each other out, and this will give us ln of 2 over 10 times t is equal to the natural logarithm of 50,000. So to get t, we just need to divide by ln of 2 over 10. So t is equal to ln of 50,000 divided by this fraction, so that's the same as multiplying by the reciprocal, so it's 10 over ln of 2. So in order to know what this value is, we would need a computer or a calculator, and so this is going to give us approximately 156.096. So this is the approximate value. So this is in minutes. So after how many minutes will the population reach 1 million cells? So the answer is approximately 156 minutes. And that's our answer. For this part, we're asked to rewrite the formula in the form, so there should be an in here, in the form a at t equals a sub 0 times b to the t. That is, find the value of b. Well, actually, we've already done this because we rewrote this as an exponential in terms of the base 2. So let's do that again. So a at t is equal to 20 times e to the ln of 2 over 10 times t. And remember, we rewrote this as 20 times e to the ln of 2 times t over 10, which we then wrote as 20 times e to the ln of 2, and all of this e to the ln of 2 was raised to the t over 10, because e to the ln of 2 is 2 using the cancellation law. So a at t is equal to 20 times 2 to the t over 10. We're almost done at this point. We have 2 raised to the t over 10, but what we're looking for is something raised to the t power. So we rewrite this as 20 times 2 to the 1 over 10 raised to the t power. And now this 2 to the 1 over 10, that's our b. So b is equal to 2 to the 1 over 10. This has some meaning because we know that the population doubles every 10 minutes. And you can see that here. Every time that t increases by 10, the population size doubles, because every time this increases by 10, you'll get another factor of 2. This leads us very naturally to a definition. So if a population is growing exponentially, the length of time it takes the population to double in size is known as the doubling time of the population. In our previous example, the doubling time was 10 minutes because we were told that every 10 minutes the cells divided, so the population doubled. Let's do another example. Suppose a population is growing exponentially according to the formula you see here. A at t is equal to 30 times e to the 0.2 times t, where in this case t is given in days. What is the doubling time of this population? Okay, well, we're given an initial population, which is 30. So a at 0 is equal to 30. What we want to know is how long it takes to double. So find t so that a at t is equal to twice that, so 60. So that's our goal. Well, we have a formula for a at t. So what we want to do is we want to find a t so that 30 times e to the 0.2t is equal to 60. The first thing to do is to divide everything by 30. And then we end up with e to the 0.2 times t is equal to 60 divided by 30 is 2. Notice that we have a 2 here now. It's 2 because we're looking for the doubling time. It doesn't matter what your initial population is. The only thing that matters is that we're looking for the time it takes to double it. So whatever value we had here, we had 30 here, and so we double that to get 60. But whatever value this was in front of the exponential, we would double it. So it would be 2 times whatever that value is. And then the first thing you do is divide by that initial population size. So regardless of what that population was, so if we just started with a0 times e to the 0.2t, and we wanted that to double, we would just write 2 times whatever that value was. So the first thing we do is divide by a0. And then we have e to the 0.2t is equal to 2. So it would always be the same regardless of the initial population size. Okay, well, what do we do now? Our goal is to get this t out of the exponent. So if you ever want to get anything out of an exponent, what you do is apply a logarithm. So let's just apply the natural logarithm to both sides. ln of e to the 0.2t is equal to ln of 2. So e is the inverse of the natural logarithm. So this is going to just give us 0.2 times t is equal to ln of 2. And now we just solve for t by dividing by 0.2. So we've solved for t. T is equal to ln of 2 over 0.2. Well, we want to figure out how many days this is, and it's not so useful in this form. So we use a calculator or a computer to evaluate this. And this is approximately 3.4657 days. So what is the doubling time of this population? Well, about 3.5 days is the answer. Let's do another example. Suppose a population doubles in size every day. So the doubling time is 1 day. If the population starts with only 10 individuals, how many days until it reaches 100,000? Okay, so in this case, we know that we're using an exponential model. So a at t is equal to a sub 0 times e to the kt. Now a sub 0 we already know, because it starts with 10 individuals. So a sub 0 is equal to 10. So a evaluated at t is equal to 10 times e to the kt. What else do we know? We know that it doubles in size every day. we still need to figure out what k is, so we're going to have to use this information that the population doubles in size every day to figure out what k is. Well, we know that it starts at 10, so a at 0 is 10, but we know that it doubles every day, so a at 1 is twice that, which is 20. So this is what we're going to use to figure out what k is. Just plug that into here. So a at 1 is equal to 10 times e to the k times 1. And this is equal to 20. This equation will tell us what k is. Basically, we just solve for k. We have 10 times e to the k equals 20. Divide everything by 10, and you have e to the k equals 2. We want to solve for k, so we need to get it out of the exponent. And the way you do that is apply a logarithm. In this case, we'll apply the natural logarithm. ln of e to the k is equal to ln of 2. So ln is the inverse of the exponential with base e. So we use the cancellation laws to get k on the left. This is equal to ln of 2. And now we know the value of k. So we can write down our formula. A at t is equal to a sub 0, which we know is 10, times e to the kt, but k is ln of 2 times t. It might help us if we rewrite this a little. Remember that e to the ln of 2 times t is equal to e to the ln of 2 raised to the t. Because when you take an exponential and raise it to an exponent, that's like multiplying the exponents together. So e to the ln of 2 raised to the t is e to the ln of 2 times t. But e to the ln of 2, that's equal to 2. So that tells us that a, evaluated at t, is equal to 10 times 2 to the t. And this is our formula. Now that we have a formula for the size of the population after t days, we can answer the question that we're actually asked here. We're asked how many days until the population size reaches 100,000. So let me just draw a line here to separate the left and right sides of this page. And we have a formula for the size of the population after t days. So that's 10 times 2 to the t. And what we want is we want to find the value of t so that a evaluated at t is equal to 100,000. Well, a at t is given by this formula right here. So we want to find a t so that 10 times 2 to the t is equal to 100,000. Or if we divide by 10, 2 to the t equals 10,000. Again, we want to get something out of the exponent, and the way that we do that is use logarithms. So let's just use the natural logarithm. ln of 2t is equal to ln of 10,000. One of the properties of logarithms is that if you have a logarithm where the argument has an exponent, you can take the exponent out. So we can take this t and we can bring it out in front. So in other words, we have t times ln of 2 is equal to ln of 10,000. Now in order to solve for t, we just divide everything by the natural logarithm of 2. And that tells us that t is equal to ln of 10,000 divided by ln of 2. This value is approximately equal to 13.2877. So in other words, it takes just over 13 days. And that's the answer to our question. Let's look at another definition. This one's related to the one before. A doubling time told us how long it took for a population to double in size. Now we're actually looking at exponential decay instead. So if a substance is decaying exponentially, the length of time it takes for an amount of substance to decrease to half its size is known as the half-life of the substance. Let's look at this example. On the 26th of April 1986, the Chernobyl nuclear power plant in Ukraine experienced what is often considered the worst nuclear disaster in history. One of the sources of radiation released into the atmosphere was cesium-137, which has a half-life of approximately 30 years. Assume the amount of cesium-137 in the area around Chernobyl is modeled by an exponential model. In other words, a at t is equal to a sub 0 times e to the kt, where a0 is a constant and k is a constant. T is the number of years since the disaster. So based on the information that we have, we want to determine the value of what we call the decay constant k. Okay, so what do we know about this? One thing that we don't know is the value of a0. We're not given that information. We do not know this value, but that's okay. We're still going to be able to determine the value of k. So how are we going to go about doing this? Well, what do we know? We know that the half-life is approximately 30 years. So half-life, let's just write it down, is approximately 30 years. So whatever the initial value is, we know that after 30 years, so a at 30 is going to give you half the initial value. So it's going to be a sub 0 over 2. But we know that there's a formula that looks like this that tells us how to compute the amount after 30 years. So a at 30 is equal to a sub 0 times e to the k times 30. So a at 30 is equal to a sub 0 over 2, but it's also equal to a sub 0 times e to the k times 30. So these two quantities are the same. So a0 over 2 is equal to a0 times e to the 30k. Let's write it like that. Notice we can divide everything by a sub 0. Then we'll have 1/2 is equal to e to the 30k. Or in other words, 30k is the power of e that gives us 1/2. We can therefore write this as a logarithmic equation. 30 times k is the power of e, which is natural logarithm, that gives us 1/2. Or in other words, k is equal to ln of 1/2 divided by 30. If we compute this using a calculator or a computer, we'll find that this value of k is approximately equal to minus 0.023. K is a negative number because this is representing decay. This is exponential decay, so k is a negative number. It might not look like a negative number here because we don't have a negative sign, but ln of 1/2 is in fact a negative number. In fact, as a little note, let's write down ln of 1/2 is equal to the opposite of ln of 2. So k is equal to the opposite of ln of 2 divided by 30, which is approximately negative 0.023, which we already computed up here. So we can see that k is a negative number, which we expect because this is exponential decay. So we were asked to determine the value of the decay constant k, and we've done that. Let's move on to part B of this problem. In what year will only 10% of the original amount remain? So what we want to do is find t so that a at t is equal to 0.1 of the original amount. We don't know what the original amount was, but we're only interested in finding 10% of that, and that's enough information because we have a formula for a at t, and it's in terms of a0. If we just go back to the previous slide, here's our formula right here. We just found out what k was. So let's write this out. So a at t is equal to a sub 0 times e to the kt, where k is equal to the opposite of ln of 2 over 30. We'll plug that in later. What we want to do is we want to find a value of t so that this quantity right here, a sub 0 times e to the kt, is equal to 0.1 times a sub 0. In other words, 10% of the original amount. So we want to find t so that a sub 0 times e to the kt is equal to 0.1 times a sub 0. Remember that k is known to us. It's this number right here. I'm just leaving it as k just to make it easier to write down right now. So the first thing to do is divide everything by a sub 0. Then we'll have e to the kt is equal to 0.1. So the next step is to get this t out of the exponent. So what we're looking at here is k times t is the power of e that gives us 0.1. So let's rewrite this as a logarithmic equation. K times t is the power of e, which is the natural logarithm, that gives us 0.1. Finally, then, we just divide everything by k. T is equal to ln of 0.1 divided by k. But we actually know what k is. So we take this value for k, right here, and we just plug that in here. So t is equal to ln of 0.1, and all of this is divided by the opposite of ln of 2 over 30. Or if you prefer, you can write this as ln of 0.1 multiplied by the reciprocal. So it's 30 over minus ln of 2, like so. However you write it down, we can compute it using, for example, a calculator, and we get that this is approximately equal to 99.6578. So in other words, approximately 100 years. So 100 years after the original event, we should expect to have 10% of the original amount. So we recall that the original event happened in 1986. So in 2086, we expect to have the radiation levels down to about 10% of what they were initially. Next, let's consider Newton's law of cooling. Let's state it as a theorem. Suppose a heated object having a temperature of T sub 0 degrees is placed in a cooler environment with an ambient temperature of T sub s. The S stands for surroundings, so this is the temperature of the surroundings. In particular, we're assuming that the object is hotter than the surroundings. Then the temperature of the object will decrease over time, and we can have a formula given to us by Newton's law of cooling that says that the temperature of the object after t units of time is T, capital T at t, so this is the temperature after lowercase t units of time, is equal to A times e to the kt plus t sub s. Here A is T0 minus Ts, so it's the difference between the initial temperature of the object and the surrounding temperature. K is what's called the rate of cooling of the object, and it's a constant. Newton's law of cooling tells us that the difference between the temperature of the object and the ambient temperature decays exponentially. If we look at the formula from Newton's law of cooling, if you subtract T sub s from both sides, then you have this equation. Capital T at lowercase t, that's the temperature of the object after t units of time. And T sub s is the temperature of the surroundings. We're assuming that the temperature of the surroundings is remaining constant. So what you're looking at here is the difference between the temperature of the object and the temperature of its surroundings. And what Newton's law of cooling tells us is that this decays exponentially. So in particular, k is a negative number. Notice that A is T sub 0 minus T sub S, where T sub 0 is the initial temperature of the object. So in other words, this A is equal to the initial temperature difference. There's also a Newton's law of heating, which is essentially the same theorem, but it imagines instead a cool object being placed in a warmer environment. In that case, everything is still the same, except the order of these two terms is the opposite. So in other words, you'd look at the temperature of the surroundings minus the temperature of the object, because in that case you're assuming that the temperature of the surroundings is higher. Either way, Newton's law of cooling/heating tells you that the difference in the temperature is decaying exponentially over time. Let's look at an example. A pizza is taken from an oven heated to 400 degrees Fahrenheit and placed on the counter in a kitchen with ambient temperature 75 degrees Fahrenheit. Suppose that after 1 minute, the internal temperature of the pizza is 290 degrees Fahrenheit. Determine the value of the cooling rate K. So in particular, we're assuming that we have the formula given to us by Newton's law of cooling. So capital T at lowercase t is equal to A times e to the kt plus the temperature of the surroundings. So we know what T sub s is. T sub s is the temperature of the surroundings, so it's 75 degrees. What about A? A is the initial temperature difference, so that's T at 0 minus T sub s. The initial temperature of the object is the same as the temperature of the oven, so it's 400 degrees minus 75 degrees, which is 325 degrees. So that gives us A. So capital T at lowercase t is equal to 325 times e to the kt plus the initial temperature, or the ambient temperature, which is 75 degrees. This is our formula. Well, almost. We still need to figure out what K is. That's actually what we're asked to find. So how are we going to do that? Well, there's one additional piece of information we haven't used yet. We're told that after 1 minute, the internal temperature of the pizza is 290 degrees. So T at 1 is equal to 290 degrees. But from our formula, if we plug in t equals 1, we have 325 times e to the k times 1 plus 75. 325 e to the k plus 75. So using the formula, we know that t at 1 is given by this expression, 325 times e to the k plus 75. But we're also told from the problem that after 1 minute, the temperature of the object, the pizza in this case, is 290 degrees. So that means that these two quantities must be the same. So 325 e to the k plus 75 is equal to 290. Now we want to solve for k. So the first thing to do is to subtract 75 from both sides. Then we'll have 325 times e to the k is equal to 290 minus 75. That's 215. The next step is to divide by this 325. So we'll have that e to the k is equal to 215 over 325. So k is the power of e that gives us 215 over 325. So if we write that as a logarithmic equation, we have that k is the power of e that gives us 215 over 325. And so that's our value for k. We can plug this into a calculator, and that will tell us that this is approximately equal to minus 0.413. And that's our answer. We shouldn't be surprised that it's negative because, after all, this is exponential decay. Let's move on to part B of this problem. What is the internal temperature of the pizza after 10 minutes? Well, we have a formula right here T after t minutes, the temperature after t minutes, is 325 times e to the k, but this is our value for k right here. So let's write minus 0.413 times t plus 75, like so. So if we want to find the internal temperature of the pizza after 10 minutes, that's simply t evaluated at t. T is equal to 10 in this case, so let's just highlight it, is equal to 325 times e to the minus 0.413 times 10 plus 75. So that's 325 times e to the minus 4.13 plus 75, and this is approximately equal to 80.2269. So the internal temperature of the pizza after 10 minutes is just over 80 degrees Fahrenheit. So maybe that's a little bit too cool for your liking, so how long should you let the pizza cool if you want to eat it when it has an internal temperature of 150 degrees? Okay, so let's figure that out. So we have a formula, T at T is equal to 325 times e to the minus 0.413 t plus 75. We want to find a value of t, so that, let's write this down, find lowercase t so that t at lowercase t, so the temperature after t minutes, is 150 degrees Fahrenheit. So in other words, we want 325 times e to the minus 0.413 t plus 75 to equal 150. The goal here is to solve for t. We want to solve for that value. So how do we do it? Well, the first thing to do is to get t isolated. So we'll do that by isolating the exponential. So the first thing we're going to do is subtract 75 from both sides. So then on the left we'll have 325 times e to the minus 0.413 t equals 150 minus 75. 75 is half of 150, so we'll just be left with 75. Now we divide by 325 on both sides. So e to the minus 0.413 t is equal to 75 over 325. What does that tell us? That tells us that this exponent, minus 0.413 t, that's the power of e, which is the natural logarithm, that gives you 75 over 325. So t is equal to ln of 75 over 325 divided by minus 0.413. And once again, we'll have to rely on technology to tell us what that actually is, and this is approximately 3.55045. So if you want the pizza to cool to 150 degrees Fahrenheit, then let it sit for about 3.5 minutes. The final model that we'll look at is known as the logistic growth model. A population is described by a logistic growth model if the population size f at x after x units of time is given by a formula like this. F at x equals c divided by 1 plus a times e to the minus bx. C is a constant. It's an upper bound on the population size, which is called the carrying capacity or the limiting value. The values of a and b are constants that are determined by the initial population size and the growth rate, although they aren't equal to these things. This is a graph of a logistic model, or a logistic curve. You can see at time x equals 0, and shortly beyond, it starts looking like exponential growth, but it starts leveling off very quickly as we reach the carrying capacity. The carrying capacity is a horizontal asymptote, which represents a limiting value. In this image, the curve approaches c as x approaches infinity. In the other direction, we have that the population curve is approaching the x-axis, or y equals 0 as x approaches negative infinity. That doesn't really have much meaning for us in terms of population models, because x representing negative time doesn't necessarily have any meaning for us. Let's look at an example. Suppose a population of endangered deer in a conservation park consists of 18 individuals. So that's our initial population. It is believed that in this conservation park, the deer population will satisfy a logistic model with carrying capacity 1,000. Assume that after 1 year, 30 deer live in the conservation park. So determine a formula for the logistic model that describes the population. How's this going to work? Well, we already know what the formula is going to look like. It's going to be f at x equals c for the carrying capacity divided by, and then we just put this in the denominator, 1 plus a times e to the minus bx. 1 plus a times e to the minus bx. At this point, we don't know what a and b are. In fact, that's what we want to determine. We already know c. C is the carrying capacity, and we're told that the carrying capacity is believed to be 1,000. So c is equal to 1,000. So that tells us that f at x is equal to 1,000 divided by 1 plus a times e to the minus bx. We need to determine what the values for a and b are. We can determine these values because we know what the initial population is, which is 18, and we know that after 1 year the population will be 30. So that tells us that f at 0 is equal to 18, the initial population, and f at 1 is equal to 30. This information gives us 2 points that the curve passes through, and that will be enough for us to figure out what a and b are. Let's start with f at 0 equals 18. F at 0 equals 18. We're just going to plug in x equals 0 into this formula right there. So we'll get that f at 0 is equal to 1,000 divided by 1 plus a times e to the minus b times 0. Well, e to the minus b times 0, that's e to the 0, which is 1. So this is equal to 1. So we have 1,000 divided by 1 plus a times 1. But we know that this is 18. We know that that's 18. F at 0 is 18. So what do we have? We have that 1,000 over 1 plus a is equal to 18. So we want to solve this for a. Okay, we can do that. So 1,000 is equal to 18 times 1 plus a. We get that by multiplying both sides of the equation by 1 plus a. And then we divide everything by 18. So 1,000 over 18 is equal to 1 plus a. Subtract 1 from both sides, and that tells you what a is. A is equal to 1,000 over 18 minus 1, which is approximately 54.56. So that's the value of a. That tells us that f at x is equal to the carrying capacity, which is 1,000 divided by 1 plus 54.56 times e to the minus bx. Now we need to figure out what b is, but we still have 1 point. We have not yet used the fact that f at 1 is equal to 30. So we know that f at 1 is equal to 30, and we just plug that into here. So f at 1 is equal to 1,000 divided by 1 plus 54.56 times e to the minus b times 1, which is just e to the minus b. But we know that this is equal to 30. So now we want to solve this for b. This is going to require a little bit of arithmetic. The first thing to do is to multiply the denominator over to the other side. Or perhaps what we'll do is we'll just flip both of these rational expressions. So we have 1 plus 54.56 e to the negative b over 1,000 is equal to 1 over 30. So if these two, if this rational function or this rational expression is equal to 30, then its reciprocal is equal to 1 over 30. And now we can multiply both sides by 1,000. So if we multiply both sides by 1,000, we'll have 1 plus 54.56 e to the negative b is equal to 1,000 over 30. And then we can subtract 1, and we'll have that 54.56 e to the minus b is equal to 1,000 over 30 minus 1, which I suppose if we write 1 as 30 over 30, this becomes 970 over 30. I guess those zeros cancel and we'll just have 97 over 3. Okay, so what does that tell us? 54.56 e to the negative b is equal to 97 over 3. Now we divide by 54.56. And that gives us e to the negative b. 97 over 3 divided by 54.56. So take the natural logarithm of both sides and you'll get minus b is equal to ln of 97 over 3 divided by 54.56. And if you use a calculator to compute that, this is approximately equal to minus 0.5233. So b is equal to 0.5233. And that tells us b. Putting all of this together, we have that f at x is equal to, at least approximately, 1,000, the carrying capacity, over 1 plus a, which is approximately 54.56, times e to the minus 0.5, let's just say 2 for 2 decimals, times x. And there you have it. There's your formula. At least that's the approximate answer. We rounded off some decimals there.